Hello and welcome to the final video of the FP2 chapter Polar Coordinates, and therefore the final video of this whole module. Starter question on the screen: find the area enclosed by the cardioid with the equation r equals a 1 plus cos theta. If you've got time, and it will take you a bit of time, pause the video now and try this question. You don't need to sketch the graph to do this question, but I think it's helpful to see what's going on, so let's have a look here. A quick reminder from the previous video, we don't need to worry about this area being negative. It's not. In a polar form, we're going from an angle, integrating around to another angle. So long as we don't have any negative radius points, which we don't in this case, we're okay to go all the way around. We don't need to worry about negative areas. We do, however, need to know the formula. A is equal to half integral from a to b r squared d theta. In this case, we're going all the way around, so we've got theta equals 0 all the way around to theta equals 2 pi. So we've got a half from 0 to 2 pi r squared, which is a squared, I'll put that out the front, 1 plus cos theta all squared d theta. Now we need to expand that out, so we've got a squared over 2 from 0 to 2 pi of 1 plus 2 cos theta plus cos squared theta d theta, and then I'm going to change that cos squared using the identity we had on the previous video. A squared over 2 from 0 to 2 pi 1 plus 2 cos theta plus a half cos 2 theta. Now, of course, I can add that onto here and make that 3 over 2, and then I can integrate. So we've got a squared over 2, and we've got 3 over 2, so that's 3 theta over 2. 2 cos theta is just 2 sine theta, and then a half cos 2 theta becomes a quarter sine 2 theta. All of that from 0 to 2 pi, and now we see the wonders of sine, because for 2 pi and 0, these are both 0 for both of these. And of course for 0, this is also 0. So out of our 6 terms here, 5 of them are 0. So we've got a squared over 2. I'll make that really clear for the examiner by putting 3 times 2 pi over 2, so that's 3 pi plus 0 minus 0 plus 0 plus 0. And I would write that in an exam just so the examiner can see you know these 5 terms are 0 when you put these limits in. Tidying all of that up gives us the final answer of 3 pi a squared over 2. And that is the area enclosed by this curve. As promised, in this final video we're going to take this a little bit further and calculate the area between two polar curves. To find the area between two polar curves, you need to evaluate 2 separate integrals. The new challenge here is to identify the regions that you need and the limits of those regions. For example, here we've got several different sections. If you wanted this little section down here, for example, you would need to integrate from minus pi by 2 around to the point where the two curves intersect, and you would need to find that by putting them equal to each other and solving. Then you would need to integrate from 0 on the blue curve up to that same point, and take away that little section to leave you this section here. But that's not a very common question on this course. What's far more common is to find this area here where the two curves overlap. To do that, you're almost always going to be adding rather than subtracting, because what we're going to have to do is split this where they intersect again, that same point, and the point over here, and then integrate from the initial line on the blue curve up to where they intersect, and that will give you this little bit here in blue. Then switch to the red curve and integrate from where they intersect up to pi by 2, and that will give you this region here. Then of course you'll have to add them together to get that right hand half, and then often you'll have the option here to double that with the symmetry of the curve, but not always. So you could also then continue on to find this one with this intersection point and this section here from this intersection point again down to pi. So use the symmetry to help you where you can, but be aware it might not always be possible. Everything else in terms of the notes are the same as the previous video. We're using the same formula, we just need to be a little bit more careful about the regions we're using and the limits of those regions. So straight into the examples. Find the exact area of the region which lies within both of the curves with equations this and this. This is another way of saying where they overlap, here in grey. Very similar to what we just had, but go in the other direction. We need to know this intersection point here, so that we can integrate from the initial line on this curve here, r equals 2 plus cos theta, to this intersection point to get this one here, which I'll call region 1. And then from this intersection point on the other curve, r equals 5 cos theta, around to the line theta equals pi by 2, to get this region in green, which I'll call r2. Then we add r1 plus r2 to get this whole bit here, multiply that by 2 to get the full area. So I'll start by writing r1 plus r2 equals, and then later when I double that, I'll use a for the full region. So that is equal to half times the integral from 0 to this point here of 2 plus cos theta all squared d theta, plus a half from this intersection point to pi by 2 of this curve, 5 cos theta all squared d theta. No doubt you've noticed I have not yet figured out what this point is. So for this point here, I'm going to call theta is equal to alpha. Whatever that angle is will go here and here. To find that, I need to find where these two curves intersect. So we've got 2 plus cos theta is equal to 5 cos theta. Rearranging that gives us cos theta equals a half. And I obviously want the smallest positive value, otherwise I'll get this one down here. So theta is equal to pi by 3. So that goes here and here. Now I need to square my brackets, set myself up for the integration. This is going to give me 4 plus 4 cos theta plus cos squared theta, which is a half, plus a half cos 2 theta d theta, plus a half from pi by 3 to pi by 2 of 25 cos squared theta, which again I'm going to change into a half plus a half cos 2 theta. 4 plus a half here gives me 9 over 2, and I'll bring this 25 out in front to give 25 over 2 in front of the integral there. Now I'm ready to integrate with respect to theta on both, and that will give a half 9 theta over 2 plus 4 sine theta plus a quarter sine 2 theta with the limits 0 to pi by 3 plus 25 over 2 times theta over 2 plus a quarter sine of 2 theta with the limits pi by 3 to pi by 2. Here again we've got quite a few zeros coming out, but not all zeros. When this comes in as a 0, all of them will be 0. When this comes into the sine theta here and the sine 2 theta here will both be root 3 over 2. Same over here for this one, and a 0 again for this one. But don't forget the thetas here. These will not be 0 except for this one. So all of that will give us a half 3 pi by 2 plus 2 root 3 plus root 3 over 8 minus 0 plus 0 plus 0 plus 25 over 2 times pi by 4 plus 0 minus pi by 6 plus another root 3 over 8. And if you go through the process and tidy all of that up, you get 43 pi by 24 minus a root 3 over 2. The last step then is to remember that this is only half of what we need, and in order to get the full thing we need to times this by 2. So the final answer in yellow, the area is equal to 2 times r1 plus r2, which is 43 pi by 12 minus root 3. And that is the final answer for the shaded area here. The second and final example is to find the area of the finite region enclosed by the curve with equation this that lies entirely within the curve with equation this. And again, this is just another way of saying where these two curves overlap. Again, you could do this without a diagram, but I think it's much easier to visualize what's going on if you can sketch the curves. These two are the two that we had in the notes, and we are indeed going to find this bit here. So we're going to do exactly what we had before. We're going to find this point of intersection here, so that we can find this region on the red curve and this region on the blue curve. To find where they intersect, we need to make them equal. So 1 plus sine theta is equal to 3 sine theta. Very similar to the last one. This will give us sine theta equals a half. So theta will equal pi by 6 radians. For the blue curve, we're going from the initial line, theta equals 0, up to this point, and then for the red curve, from this point up to pi by 2, and then we'll take all of that and double it to get the full region. To help the examiner understand what I'm doing, again, I'll call that R1 in blue, and this one R2 in red. But in this case, I'm going to do it slightly differently, and I'm going to say A is equal to 2 times R1 plus R2 right at the beginning, so I don't need to worry about doing that at the end. And then you can choose which way you prefer when you're doing your own questions. That's 2 times a half of the integral from 0 to pi by 6 of the blue curve squared, 3 sine theta all squared d theta, plus a half from pi by 6 to pi by 2 of the red curve all squared. And one reason for doing this at the beginning rather than at the end is not to forget to do it, and the other reason is because those halves in there cancel quite nicely with the 2. Squaring my brackets, getting ready to integrate, we've got from 0 to pi by 6 of 9 sine squared theta, and I'm going to change that sine squared theta into a half minus a half cos 2 theta, plus our second integral, pi by 6 to pi by 2, 1 plus 2 sine theta plus, and again I'll change that straight away into a half minus a half cos 2 theta d theta, and as we had previously, I'll get rid of that 1 there and add it on here to make 3 over 2. I'll also open this bracket to make that a 9 over 2 there and there. Now we are ready to integrate. We'll get 9 theta over 2 minus 9 over 4 sine 2 theta from 0 to pi by 6 plus 3 theta over 2 minus 2 cos theta minus a quarter sine 2 theta from pi by 6 to pi by 2. So the first one gives us 3 pi by 4 minus 9 root 3 over 8 minus 0 minus 0. And then we have 3 pi by 4 minus 0 minus 0 minus pi by 4 minus root 3 minus root 3 by 8. And if we tidy all of that up, we get the final answer of just 5 pi by 4. And that is the final example of the final section of the final chapter of FP2, which means you can now practice all the questions from exercise 8C, the review exercise for chapter 8, review exercise 2, which is the second half of the book, and the exam practice at the end. Basically everything. Lots of practice for you there. Well done for persevering through the module. Maybe I'll see you in FP3.